Good morning, everybody. As you have probably figured out by now, I am not here today. I'm at home sick while one of my kids got sick over the weekend, and she's not feeling very well, so I'm staying home with her today. But when I'm not here, luckily for you guys, I have a way to record class. You still get your daily dose of me, even though I'm not physically here, which I know makes most of you very, very happy. So, what we're going to do here, we'll take a couple minutes and go over some of the things that you need to know about the next couple days of class, do a little bit of review, and then hopefully get you ready for your test tomorrow. So, as I just kind of mentioned, if we go to the calendar and then go to the week of October 14th, test is still scheduled for tomorrow over work and energy, not over significant digits. I'll change that on the calendar, so don't worry about that, but just over work and energy. So before we get started with doing the formal review stuff, I wanted to make sure you understood what you have available to you so that you can study and what you need to do to get ready. This unit started back on Monday, September 30th, and we introduced the ideas of energy, and then we talked about mechanical energy. So we started off with a set of slides that looked like this, where we talked about different kinds of energy and what those different kinds of energy represent and descriptions of them a little bit. Sorry if that just sounded a little loud. I moved the microphone. So, this set here, you won't be responsible for a whole lot on this page. Just, basic, what are these different kinds of energy and stuff like that. The next outline that I gave you, though, looked like this, and it said Introduction to Mechanical Energy and Work. I should highlight that. Introduction to Mechanical Energy and Work. Two-sided outline. The one side had a bunch of definitions about mechanical energy and kinetic energy and potential energy. The back side briefly talked about work up at the top, but then had these different pictures representing situations, and we talked about whether that was work by the physics definition or not. After we completed that outline, I gave you this page that first had the pictures of the three cars up at the top with the changing speeds, and then we talked a little bit about how does that affect the amount of work that's done. Later on, we talked about these balls on this ramp or these steps and how that affects the amount of energy. And then later on, we talked about the box sliding down this ramp and how we can use that to calculate the amount of energy it has at the bottom. All of these relating to work and mechanical energy concepts. Once we finished that intro to mechanical energy and work, we started in on conservation of mechanical energy. So I gave you a new outline, and it was titled Conservation of Mechanical Energy. Two-sided outline. The first side basically went over the ideas of conservation of mechanical energy. We talked about this lady jumping out of the building when it was on fire. And on the back side, we got into non-conservative force and what non-conservative force does to the energy of an object and how does friction affect the energy and all those fun things. That, then, once we finished up those things, I gave you this sheet that had two sets of problems. But remember, I told you that I had a change of heart, and this whole bottom part here, we're just going to get rid of, like it doesn't exist. But up at the top, there are some problems dealing with conservation of mechanical energy where we use the energy at one location to determine the energy at a different location, and then use that number to determine a height or a speed, and we'll go through another example of that today. So those are the things that I've given you up until this point. In your hands right now, you should have a new sheet that says Conservation of Mechanical Energy Topics. So I wanted to take a couple minutes and go over this sheet. Then we'll talk about the test in general terms, hopefully prepare you for that. The first part of this sheet just deals with conservation of mechanical energy ideas. So I'm going to take this and grab this part here and put it on this page. Now remember, we said that conservation of mechanical energy only applies when there are conservative forces, and only conservative forces acting on the object. We said that there were two kinds of conservative forces. There is gravity, and then there are elastic forces, like springs and bungee cords and trampolines and stuff like that. So in the setup for this part here, it says use your knowledge of mechanical energy conservation to complete the following diagrams. In each case, assume that friction and air resistance can be ignored. So when it says assume that friction and air resistance can be ignored, we're going to go with that basically then either gravity or elastic forces are the only forces that are acting on that object, and therefore we can use the ideas of conservation of mechanical energy to then solve for what we need to solve for. So if we first take a look at this pendulum raised to a certain height, we don't know how high it was raised, but we do know that when it was raised this high, it had 10 joules of potential energy. Once it has those 10 joules of potential energy, if friction and air resistance are ignored, and there's no other forces except for gravity acting on that object, now we can assume that mechanical energy is conserved. So we talk about the idea that gravity pulls this pendulum down towards the middle, and as it pulls the pendulum down, potential gravitational energy decreases because that object gets lower, but then kinetic energy will increase because the speed of that object goes faster. So if it goes down to a height where now potential energy is only equal to 2 joules, we can then assume that kinetic energy has to make up the rest of the original total because the total amount of mechanical energy has to be conserved. So we can say that kinetic energy is equal to 8 joules. In the third picture, this is going to be, because that string is straight up and down, that's going to be the lowest point. We can also figure it to be the lowest point because it told us that potential energy is equal to 0. But once again, because only conservative forces, only gravity acting on that pendulum, the total amount of mechanical energy has to be the same, so kinetic energy has to then be 10 joules. In the fourth picture, it doesn't give us potential or kinetic energy, but luckily for us, it gave us these little dotted lines to represent height. This dotted line is where the pendulum originally started back over on the left-hand side. If we watch it swing back down, it goes below that dotted line, but then it comes back up and eventually ends up right back on that dotted line. Because mechanical energy is conserved, if that object got back up to this height, if it started with 10 joules of potential energy, it has to end up with 10 joules of potential energy again. But because mechanical energy is conserved, there can only be a total of 10 joules. Therefore, if there's 10 joules of potential energy, there has to be 0 joules of kinetic energy. All right. Based on that discussion, you should be able to fill out the rest of this sheet. So why don't we take a minute or two, just on your own, fill out the rest of the spaces on this sheet based on those ideas that we just talked about. I will slowly start putting them up here on the board so you can see what I did and what you did. So let's take about 2 minutes, fill in the part for this ball rolling down this ramp and this guy high diving from the top platform. Go. Okay, if you have not been watching the screen intently, I have gone through and filled in the things that I need to fill in. So there's the numbers for the rest of those problems. The ramp here with the ball rolling down the ramp, and this guy coming down from the high dive. Hopefully we're good there. The next part of the problem set, hold on, stand by. The next part of this problem set deals with a ball rolling down a two-sided ramp. So I'm going to grab this here and put it into its own page so I can write on it. And we'll go. It says the figure below shows a 2-kilogram ball as it rolls down a ramp. The downslope of the ramp is frictionless. I'm going to highlight that. But the upslope has friction. So if the downslope is frictionless, that means from here all the way to here, no friction, but it says that the upslope has friction. So this part that I'm highlighting here in pink, there is friction. So based on that, let's take a look at these questions. So it says, how fast will the ball be traveling at the bottom of the ramp? So if it says how fast, it wants us to know the velocity of this object. It already told us earlier on that this ball, let me move that circle, that this ball has a mass of 2 kilograms. So we know that its mass is 2.0 kilograms. Here at the picture, at the bottom of the ramp, it tells us that this object has 50 joules of kinetic energy. So earlier in this unit, we learned that the amount of kinetic energy that an object has is determined by its mass and its velocity squared. So if we know the amount of kinetic energy it has, and we know its mass, we should be able to figure out its velocity. And we can do that. So we plug 50 in here. 1/2 is still 1/2. I can't change that. Times 2 for the mass. Actually, I should go 2.0, but that's all right. And then v is our unknown, but it's still square. So now, mathematically, we can figure out how fast this object was going. First, I would probably multiply 2 by 1/2. That's pretty easy to do first. That just gives me 1. And then I would divide both sides by that 1 to get v squared by itself. And when I do that, I get v squared equals 50. But I don't want v squared, I want v. So I can take the square root of v squared and turn that into v. But if I take the square root of v squared, I have to take the square root of 50. So I'm going to do that real quick, and I'll give you what the answer is. All right, when I plug that into my calculator, I got v is equal to 7.07106. But looking back at my numbers, one certain digit and one uncertain digit in the mass, one certain and one uncertain digit in the kinetic energy, so I should round this to 7.1. Okay, the next question says, how tall is the ramp? So, if it's asking for something how tall, it wants to know h, right? The height of that ramp. Well, we learned earlier in this unit that the height of an object will help determine its gravitational potential energy. But in order to know that, we need to figure out, well, the gravitational potential energy depends on height, but it also depends on the mass of the object, the effect of gravity at that location as well. So if we go back to this, go back to the ramp, the yellow part of this ramp, we said, is frictionless. So if it's frictionless, gravity is the only force that's acting on that ramp, and it's causing the object to change from potential energy, or causing the energy to change from potential into kinetic. So, at this point, halfway down, well, if at the bottom of the ramp it had 50 joules of kinetic energy and 0 joules of potential, but there was no friction on the way down, that means it had to have started with 50 joules of potential energy back up at the top. And just to complete our picture, although we don't need it to solve this problem, 25 joules of kinetic energy right in the middle, because there were 25 joules of potential energy at that point, and the total has to remain the same because mechanical energy is conserved, because gravity is the only object or only force acting on that object. So that being said, now we know how much potential energy this object had at the top of the ramp. It's 50 joules. We already established that the mass of that object is 2. A long time ago, we learned that the effect of gravity, or the acceleration of gravity here on Earth, is 9.81. So now the only unknown that we have in this equation is the height. So we start plugging in things that we know: 50 for the potential energy, 2.0 for the mass, 9.8 for the gravity, and then h is still my unknown. The height is still my unknown. So now mathematically, first thing I would do is multiply 2 by 9.8, and when I do that, I get 19.6 h on that side, 50 still on this side, and then to get h by itself, I need to divide both sides by 19.6. So I take 50 divided by 19.6, and my calculator gives me h equals 2.55102, blah, blah, blah. One certain, one uncertain digit in the potential energy, one certain, one uncertain here in the mass, one certain, one uncertain in the effect of gravity. So I'm going to round this to 2.6 because, right, if I go certain, uncertain, right after that's a 5, so I'd have to round that 5 up. On the test, I am not going to hold you responsible for rounding properly. I only need you to get the right answer. We'll talk about rounding properly more shortly when we talk formally about significant digits. I have been introducing you to this concept, but it's not official yet. So that would be the height of the ramp, where it starts. The last question says, draw the possible highest position of the ball on the up trip. Well, we already established that the upslope, right, the upslope has friction, and I highlighted that part over here, right? So now that there's friction acting on that object, friction does negative work. But more importantly, friction is a non-conservative force, meaning that when it does work on an object, it's going to change mechanical energy into non-mechanical energy. Usually that non-mechanical energy is heat. But more importantly to the location of our ball, right? Back in the pendulum problem that we did on in the first part of this sheet, when there was no friction or air resistance, that pendulum got right back up to the height that it started from, because it had to end up with the same amount of potential energy over here as it did over here, because it didn't lose any. But on the ramp, that's not the case. So while I can't officially put it anywhere, the only place you can't put the highest position of the ball is right back up here at the top of this ramp, because it'll never get back to the top of that ramp. Because when it gets back to this side, it will not have 50 joules of potential energy. It can't, because friction has turned some of that energy into heat energy. So we could draw it here or anywhere else on this ramp. It really depends on how much friction there is. But it just can't be at the very, very top. Last part of this problem set, if you flip it over to the back, it shows a picture of a pulley lifting a very heavy weight, which we call a pile driver, to a certain height. And it says the picture on the left shows a pile driver raised to height that gives it 100,000 joules of gravitational potential energy. And I know that that's not what it says here, but that's okay, whatever. The question says, is it capable of doing 10 or 100,000 joules of work when it hits the object at the bottom? And the answer is, well, it depends. If gravity was the only force that was acting on that object from this height here that we raised it to that height there, sure. Because at the end, the potential energy first gets converted into kinetic, but then that kinetic energy does work on this, I don't know, whatever it is, a stake or something like that, to pound it into the ground. But if there's something other than gravity acting on it on its way down, like air resistance or friction, there's friction generally with this pulley right here and air resistance there, the best we could probably say is that it would do less than 100,000 joules of work, because friction turns some of the original PEG into heat. And that means it can't do the same amount of work as the energy it contains. Okay, to wrap this up, going back to the calendar. Oh, stand by. Going back to the calendar, okay, like I said, test is still going to be scheduled for tomorrow, Tuesday, October 15th. The test is going to look very similar to the test that you took the previous time. There's going to be multiple choice questions. There's going to be short answer questions worth 2 points. There's going to be possibly an extended response question worth 4 points. The one big difference that there's going to be is that there is going to be some calculations that you have to do, right? You're going to have to use the conservation of energy idea to solve for a height or solve for a velocity, so make sure you look over problems like that. If you have not done so already, going back to the home page, underneath this link for objective sheets, Unit 2, Introduction to Energy and Work. And if you pull that up, there's your objectives for this unit. Like I said, if you have not done so already, make sure that you do that tonight. If you have questions, email me, even if it's during school today. I should get back to you sometime today. If not today, I will definitely get back to you tonight, so that you can get those questions answered. I should be in school early tomorrow, although I do have a meeting at 7:15, should be done by 7:30, so anytime after 7:30 you should be able to find me in this room if you have questions about tomorrow's test. All right? Good luck with your studying, and hopefully if everything goes well, I will see you guys on Tuesday.